Let's keep up with the momentum. What's momentum? This is a new concept. Chapter 7 was introducing energy, and there's conservation of energy. Chapter 8 introduces momentum, and there's conservation of momentum. They're very similar concepts. The difference is that, the biggest difference I think is that energy was a scalar and momentum is a vector, so that makes the momentum a bit more difficult to deal with. It's a vector equation. It's just mass times velocity. So we're going to find that this turns out to be pretty useful. So this morning on the pre-class survey, I asked a car is traveling at some initial velocity. Without turning, it then doubles its speed. How does that change the kinetic energy and the momentum? So I guess momentum is a little bit like kinetic energy in the sense that it's only if something's moving. Ke is equal to 1/2 mv squared, and momentum is equal to mv. So one is proportional to speed, and the other one's proportional to speed squared. And it makes a difference. We're going to use momentum. I'll show you how it comes in useful. Certainly, a moving boulder has more momentum than a stone that's rolling at the same speed, and it has, if it's going faster, it's got more momentum. And something that's at rest relative to you has zero momentum. We do a couple examples. If you got a 1,000-kilogram car traveling west at 25 meters per second, you would say that P is equal to 1,000 kg times 25 meters per second, comma, west. And the answer would be that P is equal to 25,000. And the units here are kilograms meters per second, and the direction is west. What about a bullet? So here, P is equal to the mass of the bullet, 0.01 kilograms, times its velocity, which is fired straight up with 1,000 meters per second, so that's 1,000 meters per second, comma, up. So I would say that the momentum of this bullet is 10 kilograms, a lot less than a car, actually. I always think of cars as being a pretty effective murder weapon. What we're going to do is 3 experiments, observational experiments with these carts. I guess maybe I'll show them first, and then we'll try to analyze them in terms of momentum and momentum conservation. So, fantastic. So there's a big reason why we use momentum, and that is because it gets conserved in these collisions. So right now I've got the cart set up so that they have what's called an elastic collision. There's a little magnetic force, which is conservative actually as it comes in. So what I'm going to do is start with, so this one is stationary. Block B is supposed to be stationary. You stay now. There we go. And then I'm going to have this cart A coming from the left with some initial speed, maybe 1 meter per second. Well, that's kind of cool. It stops while the other one takes up all its momentum. So you can think about the before and after situation there. The next experiment I want to do, same thing, B will be stationary, but I'm going to double the mass of this original cart and then send it. What do you think will happen? Goes along, keeps moving. And the other one actually goes off with a much faster speed. So somehow this one having more mass ends up causing this one to have a higher final speed than the initial speed of the more massive one. And then the third experiment I'm going to do is, I know. I wanted to do an inelastic collision. How do we do that? Do I just turn one around? Yeah, there we go. Okay, good. And then try to do it. This is where you have them going towards each other at the same speed. It's a little hard to do. Okay, I think they stop. Okay, so they both had some initial speed, and then they come to rest at the end, or pretty close to it. So I do want to work out the math and kind of try to show to you that there's a conservation of momentum here that we observationally show. So PA here is equal to 0.2 is the mass times 1 meter per second. And then PB was at rest, that's 0. So the total is P is equal to plus 0.2 kilograms meters per second. This was that first experiment I did. And then what happens at this one ended up, PA prime is 0, and PB prime picks up all that final momentum, 0.2 times 1. So P prime is equal to also 0.2 kilograms meters per second. So this is before equals after. So that's that first experiment I did. It sometimes happens in a Newton's cradle. I don't know if you've ever seen that, where you've got those balls that are hanging. One swings down, it hits the other, and then the other ones go up, while the first one just remains stationary. That's a property of elastic collisions. You've got momentum conservation and also kinetic energy conservation. But if the masses are different, then something different happens. So here, I've got to keep track of it here. PA is equal to 0.4 times 1, and PB is equal to 0. So it's easy to find without the prime. I don't like these primes because they're easy to accidentally write. Anyway, P initial is plus 0.4 kilograms meters per second. And if you were to measure the velocities carefully, you would find that this one is now going 1.2, so actually faster than the original, more massive one. And then the massive one is also still traveling to the right with plus 0.4. But if you work out the primed ones, you've got PA prime is equal to 0.4 times 0.4, so this is 0.16. And this one, PB prime, is equal to 0.2 times 1.2, and you get 0.24. So if you do the P prime, and you actually calculate 0.16 plus 0.24, when you do these experiments, you find that momentum has been conserved. So it really isn't that we just randomly wrote down m times v and called it the momentum. It does seem to be something fundamental here. In collisions, the momentum before and the momentum after are equal. Clearly, it's a vector, meaning that this is PA is equal to plus 0.2, and PB is equal to negative 0.2, so P is equal to 0.2 minus 0.2 is 0. The initial momentum of this system actually is 0, because a positive momentum cancels a negative momentum. And so if they stick together, you get P final equals 0 as well. And once again, momentum is conserved in all three of these collisions. So it looks like this, got too many equations here. The momentum of a system before and after a collision, or also an explosion, we'll talk about that a bit later, in which there is zero net force on the system, is the same before and after. So here there's just two objects. The prime denotes after the event, so P1 means the momentum of object 1 before the event, whatever happened, and then P1 prime is the momentum of object 1 just after that event. And then it's kind of like Newton's law, Newton's second law. I told you F equals ma is actually two equations. It's Fx equals max and Fy equals may, right? It's the exact same thing with momentum conservation. You conserve momentum in the x direction, and you also conserve momentum in the y direction. It's two equations. It's just all the little x's on the A29x and all the little y's on the A29y. That's how these vectors work. And you can kind of see this. There's a lot of, this textbook is filled with a lot of guns and sports, but anyway, there's a cannon, which is this gun, and then the cannonball. So the cannonball is launched with a very high velocity towards the right. The more massive cannon recoils with a smaller velocity to the left. So the cannonball gains momentum. The cannon gains the same amount of momentum, but in the opposite direction, so that if there was no momentum before that thing blasted out, because it was just sitting there, the momentum of the system is 0 right after. That momentum is not conserved for a projectile. Forget it. Momentum is conserved in these things like, collisions and stuff like that. But whenever there's a net force on an object, there's no conservation of momentum at all. And in the case of a projectile, the net force on it is gravity. So what's happening is that the momentum is constantly changing. Every second, the momentum of a 1 kilogram object that's in free fall, or it's a projectile, is going to change by 9.8 kilogram meters per second. And another thing here is that momentum is a vector, and the direction definitely matters. It's a big difference between 1 meter per second up and 1 meter per second down. The difference is 2 meters per second. Conservation of momentum is only a useful concept when you have a system for which the external net forces are 0. They sum to 0 somehow. Or maybe they're negligible compared to the internal forces. Here's the 10 kilograms rocks. What I'm going to do, Laura has a mass is 35 kilograms, stranded without a paddle in a canoe, 65 kilograms, 5 meters from the shore. She has 10 kilograms of rocks on board the canoe. If she throws all the rocks away from the shore and can throw at 10 meters per second, how fast does she get it? I put maximum speed, but I think what I was thinking is there might be some friction from the water or something like that, but what's like the theoretical speed she would get to if there was zero friction? So what I would say is that before you've got, and so what's happening here is that they're at rest. So the momentum is 0, right? And what I'm going to do is define plus x to be to the right. And then after, so I'm just doing a quick before and after sketch. What happens here is that now you've got the rocks going this way. Rocks. But then I think what could happen is that Laura and the boat could be going that way. So this is, I don't know, 1, we'll call it M1 and M2 or something like that. And so I'm hoping that she gets closer to the shore. That's my diagram. I always say draw a diagram, but the point is it doesn't have to be beautiful. It just has to get you sorting out your thoughts. So what I've tried to do here is I've defined M1 is Laura plus the canoe. So it's going to be the 35 kilograms plus 65, which I think actually equals 100 kilograms. So that's M1, and then M2 is the rocks. Okay, so that's 10 kilograms. And so, and then what I would say is that V2 prime is equal to negative 10 meters per second. This is after throwing, after the throw. Makes sense? So that's why I put the ticky thing on the V2. And then the question is, what's V1 prime? We were trying to find. So what I would say is that P equals P prime, so the sort of similar to the conservation of energy equation, isn't it? It's the E initial is E final. So the P initial is P finals, or before and after. So P1 plus P2 is equal to P1 prime plus P2 prime. So 0 plus 0, they're both at rest, is equal to MV1 prime plus M1 V1 prime plus M2 times V2 prime. So you rearrange it. V1 prime is what you're trying to solve for. It's negative M2 times V2 prime divided by M1. I think that's right. So we put negative 10 times negative 10 divided by 100. So I get plus 1. So she's going in the right direction, but a lot slower, 10 times slower than she can throw rocks. But it should get her there, right? It's only 5 meters, so get her there in 5 seconds, actually. Collision, so I just want to mention that for most collisions, the forces involved between the two objects that are colliding, like this police car and this streetcar, are much greater during the collision than any external forces. So there will probably be friction on the police car. There'll be gravity actually on the police car and the streetcar, which are pretty large forces. But during the collision itself, for that millisecond or whatever that they're colliding, that the largest force is I guess the normal force on each other. So therefore, the sum of the momentums of all the objects before the collision equals the sum of the momentums after the collision. And another example is explosion. So you've got this firecracker that you throw, and then it explodes. I would say that during that explosion, the forces on all the little fragments is very high for a very, very short amount of time. And they'll be flying out in different directions. But the momentum of all the fragments added up should equal the momentum of the object just before the explosion, if it was going or something. You can kind of see as this firework is exploding, there's sort of a downward acceleration of whatever the center of mass is. So the textbook talks about impulse, which is actually an integral, but the idea is that it's the net force times the delta time. And this is getting back to exactly your comment about newtons times seconds, which is that, we should do a units check here. Let's see if we can show it, which is impulse has units of newton second, but you should be able to show that newton seconds are equivalent to kilogram meters per second. So the trick here is F equals ma, right? So a newton is a kilogram times Acceleration is meters per second squared times seconds. So this seconds cancels this squared on the bottom, and you get kilograms times meters per second. So it works out. So a change in momentum comes from a net force delivered over a time. And that's called impulse. And impulse is also the area under the force-time curve. But if it's a constant net force, or if you use average, then this is the area you want. This is delta t is the base of this triangle, and the height of this triangle is the F net. And base times height is impulse. So this comes up in problems. Let's do a quick example, and then I'll let you guys out of here. Baseball example. Here's Shohei Ohtani. He's right now in the World Series, hitting home runs. You got initially, let's do a diagram here. Get my last thing. Before and after. So let's do before. And the thing I care about here is the baseball. So the baseball has a mass of 0.15 kilograms, and its velocity, if I'm going to define plus x is to the right, then the velocity is negative 30. And then after, hopefully he hits it to the right, but the point is v prime is what we don't know. But we do know that F net times delta x, the impulse, or delta t, sorry, F net times delta t is the impulse, is 12,000 newtons times 1 millisecond. So what this means is that delta t is equal to 10 to the minus 3 seconds. The milli stands for 10 to the minus 3. So it seems like quite a large force, 12,000 newtons, but it is possible for a bat on a ball to exert huge forces over a very, very small duration of time, thousandth of a second. So then you have to multiply times 1 over 1,000 seconds, and you get 12 Newton seconds, for example. And then you use this idea that the change in momentum is the impulse, delta t, and you can find the final speed of the ball. And remember, change is going to be p after minus p initial, so it's m, the mass doesn't change, so it's mv prime minus mv. So you can rearrange this, you're trying to find v prime, you end up with v prime is equal to f net delta t divided by m plus v. Yeah, it was v prime minus v is the change, so I'm now adding v. So it's original v plus the impulse. And don't forget, the original v was negative. And this kind of makes sense, right? It's starting off with negative. When he's hitting it with the bat, it has to first stop it from being so negative and then make it go positive. So you're going to have to subtract the 30. So anyway, you get 12 divided by 0.15 minus 30. And it does come out to be positive. I got plus 50. And the units are meters per second, because I divided by kilograms. Elastic collision, I'll just define, elastic collision is when momentum and kinetic energy is conserved. And inelastic collision just means that the kinetic energy is not conserved, but you still conserve momentum. And there's 3 kinds of inelastic collisions. There's the perfectly inelastic collision. This is when the Velcro sticks the 2 objects together. That's what I was showing you there. There's a partially inelastic collision, which just means they don't stick together, but the kinetic energy is less. For some reason, there's some sort of damage or something. That's like the general inelastic. And then there's a special thing called, textbook talks about this, explosive collision, where you get some more kinetic energy out because you've released a spring or a mousetrap or something like that. It's possible for kinetic energy to be greater at the end. Sometimes it's called the impulse momentum theorem, which relates impulse to change in momentum. I've heard it called this. And I might actually mention this. Someone asked on the pre-class survey, I'm kind of confused with the relationship between momentum and impulse. And then, so they Googled up definition of impulse, and they found 2 different definitions. One was the amount of change in the object's momentum, and the other is the product of the force applied to an object and the amount of time applied. So which is it, is the question. And I think the way it goes is that I would say the definition of impulse is that force delta t. It's an integral of the net force versus time under that curve. So it's an area. But But it turns out, due to Newton's second law, that equals the change in momentum of an object. So sometimes you see it listed as impulse is the change in momentum, because it always is. So like one's a definition and the other one's sort of a consequence of physics. But it comes up a lot. So if you've got a force that's being applied over some time, you're trying to change the momentum of something. So for example, in golf, you're hitting a golf ball, and they say, you should follow through in your swing, meaning that you should sort of extend the amount of time, I think, that the club is actually in contact with the ball, rather than trying to stop your swing short. And that would, I guess, give it more of a change in momentum, which is sort of what you want. Sometimes what you want to do, you've got a fixed change in momentum, but what you want to do is to reduce the force for some reason. This is bungee jumping. So if you jump off a bridge and then you're going to hopefully stop before you hit the ground, there's sort of two ways of doing that. There's a way the ground could exert a force on you over some very short amount of time and stop you, or you could have a bungee which would be stretching as you're falling and extend that force out. So you decrease the momentum over a long time and extend the time during which the momentum is reduced. So if you increase, you've got a fixed delta P in that case, you have to stop, but you've got delta T is longer. And this is the same with airbags and sort of crashing. Falling with style is what Buzz Lightyear does in Toy Story. So I was thinking about crashing with style. So if your car's out of control, going at some fixed initial velocity, and you have to stop, delta P is fixed. But delta P equals F net times delta T. So one could be big and the other could be small. So if you increase delta T by crashing, for example, into a bale of hay, then you can have a smaller force and it doesn't destroy your truck as much. But if you crash into a brick wall, the delta T of the collision is very, very small. So you need a large net force, and that's what hurts your car. Getting punched with style, is that you kind of, rather than if someone punches you, you really hold still, it decreases the delta T, but if you kind of let the punch move you more, you can increase delta T and again, decrease the force that you feel. You might want to, if you're the one doing the punching though, you might want to try to make that a sharp, small delta T. This is how karate expert splits a stack of bricks by bringing her arm and hand swiftly against the bricks, decreasing that delta T for a fixed change in momentum, and then delivering a huge force that breaks the bricks. As part of a safety investigation, two 1,400 kilogram cars traveling at 20 meters per second are crashed into different barriers. Find the average forces exerted on A, the car that hits the line of water barrels and takes 1.5 seconds to stop, and B, the car that hits a concrete barrier and takes 0.1 seconds to stop. Basically, you've got sort of before, which is here's your car, M is equal to 1,400 kilograms, and V is equal to like plus 20 meters per second. And then after, you've got V prime is equal to 0. It stops. And so you can find delta P is equal to F net, which is, I guess, a vector, times delta T. And delta P is going to be mass times V prime minus V. And so I guess that's equal to F net times delta T. You're trying to find F net, so it's going to be M times V final minus V initial, the change in V, divided by delta T. So for the water barrels, I would say that F net is equal to 1,400 times 0 minus 20 divided by 1.5. And I got negative. Oh yeah, that makes sense, right? It's stopping, so I guess negative 19,000 newtons. That's actually kind of high. But then the concrete barrier, F net, is equal to 1400. It's the same mass, it's the same change in velocity, so same change in momentum, but now we're doing it in 0.1 seconds, and I got negative 2800, so a lot more. So this is a greater force from the concrete. So there's an example, sort of a concrete example of using impulse momentum theorem. So now I want to talk about collisions. We talked a little bit about, we did this last time, elastic and inelastic. But what I want to focus on first is this statement on the top, which is that any collisions between two moving objects will conserve momentum, assuming that the net forces, the external forces on those objects are negligible or a lot less than the internal forces between those two objects. Also, collisions happen over such a very short little amount of time that when you do sort of an external impulse, it's always very small. So you classify collisions based on not how they conserve momentum, because they all conserve momentum. You classify them based on how they conserve kinetic energy, whether or not they conserve kinetic energy. If they do, then that's an elastic collision. The kinetic energy sum of the both particles before and after the collision is the same. And inelastic means they're less kinetic energy. So kinetic energy got used up somehow. And one of the kinds of inelastic collisions is that they stick together, and the other is that they don't. And then we talked last time about those two. If you've got, for example, a perfectly inelastic collision with things that have opposite momenta, the total momentum of the system is 0 before and after, so they stop. So a 1 kilogram mass slides along the ice, traveling to the right at 1 meters per second. It collides head-on with a second 1 kilogram mass, initially sliding to the left at 1 meter per second. So if you do 1 times 1, you got +1 for the momentum of one, -1 for the momentum of the other. Total momentum is 0 before the collision. And if they stick together, you know the final speed is 0. Collisions between these particles conserve momentum always, but they might not conserve kinetic energy, might get destroyed in the process. Something heats up. But then, if you think about a basketball, did it conserve momentum during the collision? And this is called a collision with a fixed object. And it's sort of weird because it almost does the opposite. So we know collision between two similar massed objects do conserve that momentum. P1 plus P2 is the same before and after the small little collision, assuming there's no big external forces. But when a normal sized object collides with the Earth, or even if I throw it against that wall and it collides with something that's attached to the Earth, then all of a sudden it'll really change its momentum. The momentum of the ball is certainly not conserved during this collision, right? It reverses, usually. So what happens in the case of the floor and the wall is that the Earth kind of absorbs a huge amount of momentum or provides it in some way. And the Earth doesn't. So I guess probably there is some conservation of momentum if you add the momentum of the whole Earth and the basketball, but no one can ever measure that for the Earth, so we just say it goes away. So even though we say momentum is always conserved in collisions, if one of those objects is the Earth, then it's not conserved. And then we say in an elastic collision with a fixed object like the floor, the kinetic energy of the object is conserved, so it has the same speed just before and after the collision. But the velocity has changed, and in fact, the component of the velocity perpendicular to the surface has flipped. And then if it's an inelastic collision, you also lose some speed. Impulses are generally greater when objects bounce, as opposed to just stopping. So, example, if you catch a falling flower pot from a shelf with your hands, you provide the impulse to reduce its momentum greater when objects bounce, as opposed to just stopping. So, example, if you catch a falling flower pot from a shelf with your hands, you provide the impulse to reduce its momentum down to 0. If you then were to throw that object back up again, you would be providing an additional impulse, actually of the same magnitude, and the same direction, actually, because you have to provide an upward impulse to stop it from going down, and then another upward impulse to get it going back up again. So that would be a double impulse. And that's exactly what happens when something like this basketball bounces from the floor. We have the sad and happy balls, but they can't see if that's working or not. Yeah, one of them bounces, and join on the paper. One of them, look at that one. This is like sad ball, happy ball. So for some reason, these balls have some sort of different property to them. You can also do it with there's a clay ball. It's just sort of squishy, and when it falls, it doesn't want to bounce, no matter how hard you throw it down. So some things are bouncy, others are not. Two objects of the same mass strike a flat tabletop at the same speed as shown. So maybe they were dropped from the same initial height from rest. Scenario 2, the object stops, and then scenario 1, the object bounces off the table. So you've got a rubber ball versus a clay ball or something. So the change in momentum from scenario 1 is twice as much as in scenario 2. So the impulse of the table on the object is twice as much. This is embeds. So you've got a bullet traveling at a speed of 300 meters per second, embeds in a 1 kilogram wooden block resting on a horizontal surface. And then it says the block slides. So first you shoot it with a bullet, and then it slides along the table a distance of 4 meters, and then stops. Determine the coefficient of kinetic friction between the block and the surface. You would think there might be an easier way of determining coefficient of kinetic friction without bringing out a gun, but this is what we're going to do. You've kind of got three things that's happening. Is you've got before collision, which is here's your bullet, which is like B or something like that, and it's got some VB going towards the right, and then you've got the wooden block. And so V of this piece of wood is 0. VW is 0, VB is something big, plus 300 meters per second. You were given the masses here. And then just after collision, I would say the bullet embeds. To me, that it means it sort of sticks together. So I think that this is a perfectly inelastic collision, and it will conserve momentum, but it will not conserve kinetic energy. Okay? So then what you've got is this piece of wood with a bullet embedded in it, and it's going off with some V both or something like that, or total or something. Prime is what you don't know. And then sliding. So V total is the initial speed, and it goes over there and stops some distance D, is 4 meters. And then V final is equal to 0. And that's going to be more, I think we might as well use energy for that. So the way I would do it, it's kind of the setup. I did it before I came here. How did I do it? So it's sort of two segments, a collision and then sliding. So let's do the collision first. The collision is this, P is equal to P final. So I've got the P of the bullet plus the P of the wooden block is equal to the P of the bullet final plus the P of the wooden block final. And that is going to be the mass of the bullet times the V of the bullet plus 0, because the wooden block is not moving, is equal to them together, but then V total or something like that, right? And so I can solve V total prime is equal to V MB times VB divided by the total mass. And I think rather than leave this in symbolic form, which is what I tend to do, I think I might just plug in the numbers right now just so I know how fast the thing was going before I started sliding. So I can do 0.02 is the mass of the bullet times 300 divided by 0.02 plus 1. And I get 5, and I'm going to keep 5 significant figures just because I'm paranoid about rounding error. Okay, so that's the collision part. So now we know that there's a block with mass 1.02 because it's got a bullet stuck inside it, sliding along with some initial speed, and we know the initial speed, and it goes for 4 meters. So now it's kind of like a chapter 1 to 6 problem or something, right? Well, we could kind of make it a combo. This is now the sliding, okay? And so what's going to happen is that it's going to go along, it's going to have some normal force, it's going to have mg, and it's going to have Fk. Fk is equal to normal force times mu sub k, and there's no acceleration. The y component is 0, so that means that F net y is n minus mg equals 0. You guys know N is mg, right? So basically Fk is equal to mu sub k times m times g. And then let's conserve energy. E initial equals E final. So we could do Ke initial equals Ke final, but then plus the heat that's left behind, Fk times d. This is the work done by friction. Heat equals work. We talked a little about this, about the internal energy. And this equals 0 because it stops at the end. So you got 1/2 mv tot prime squared equals mu sub k times m times g times d. Now there's m's on both sides of the equation, and you get that mu sub k is equal to v total prime squared divided by 2 times g times d. So I got mu sub k is 0.44, something like that. So there's the one-dimensional and the two-dimensional. So I'm just going to do the one-dimensional today. Consider a head-on, perfectly elastic collision of a ball of mass m1 having initial velocity v1 with a ball of mass m2 that is initially at rest. So what's going to happen is that there'll be some collision, and during the collision there might be some energy stored as elastic potential energy, but then all of it gets converted back to kinetic. So kinetic final is the same as kinetic initial, before or just after. So what you can do is that we know momentum is conserved because it's conserved in all collisions. Now we also know that kinetic energy is conserved. These are actually two independent equations. They look a little different, but the squareds make a big difference. And you can solve out. And that's what the book gives you. Okay, and it takes a little bit of math to do this. I could try to post it or something like that, but it's a good thing to have in your aid sheet, is that this is the final velocities of two balls when you know that the ball M2 was initially at rest. And what's good about this is that you can always switch to a reference frame in which ball 2 is initially at rest. So these are actually equations that a lot of physicists use even in particle accelerators and things, where you go to the rest frame of the target, and then these will be the final velocities of your two objects. The rocket moves left, the expelled fuel moves right. So cars change their velocity because of an interaction with the road. You've got static friction pushing the car forward. Even a ship in water, for example, is interacting with the water. The propeller in the ship pushes the water backwards, and the water pushes the ship forward. A rocket in empty space has nothing to push against, so if the rocket and the fuel are at rest before the rocket fires its engines, momentum is 0. But because there's no external impulses, after the rocket fires its engines, the momentum should still be 0. So what happens is that the fuel or the exhaust moves one way and the rocket moves the other way. Basically, the reason why, as you've all done, why the balloon zips away is the exhaust goes out the other way. Okay, so this is thrust. It's the force exerted on by the fuel, I guess, or exhaust on the rocket during propulsion. It's a lot, and it can change the rocket's momentum. You've initially, your system is the rocket plus the fuel. The fuel sort of goes this way. This is what I would call the exhaust, going to the left, and then the rocket goes to the right. And so this P is equal to 0, and this P prime is also equal to 0 when you add up the two things. So what we do, can you explain how we got to equation 8.78? So that's what I'm going to try to derive right now. A student was noticing that you need to kind of make a few approximations as you do this. So when we have delta M, it's much, much less than M, and so it is a little sloppy, but I can show you this way. So this is the momentum, a rocket plus its velocity plus 0. So we're changing a rocket's momentum. So if you rearrange this, you've got a change in something's velocity is equal to the mass of the fuel times the final velocity of the fuel. So you get the change in velocity of the rocket, divide both sides by delta t, and you get the acceleration of the rocket minus the mass of the fuel times this the ejected fuel divided by delta t. So this is this equation that they show you in the book. It's actually equation 8.78. I think they actually assume that the rocket is going straight up and that there's a gravity effect of Earth, so they minus off g from this. But this is if it's in deep space and then there's no g. And also now this one doesn't depend on direction. So VE is the exhaust relative to the ship. Delta M is how much fuel is being used. MR is the mass of the rocket, and delta T is the amount of time. So this is like the delta M over delta T is the rate of change of the mass of the rocket. So we'll do a quick example. A rocket is fired in deep space where gravity is negligible. In the first second, it ejects 1 over 160 of its mass as exhaust and has an acceleration of 15.2 meters per second squared. Find the speed VE of the exhaust gas relative to the air. So we've got the rocket. This is VE, which is question mark. This is the mass of the rocket or something, and it's accelerating this way. A rocket is equal to 15.2 meters per second squared. Delta T is 1 second. Delta M over M is equal to 1 over 160. So that's my diagram. Let's use the rocket equation, which is that the acceleration of the rocket is VE divided by the mass of the rocket times delta M divided by delta T, and solve for VE. So you get VE is equal to the acceleration of the rocket times the mass of the rocket divided by delta M times delta T. And that's that ratio that you were given, except it's upside down. So 15.2 times 160 over 1 times 1 second. So I got 2,400. So you need to design, I guess, the nozzle or something on your rocket to expel gases at 2,400 meters per second relative to the rocket to get this necessary acceleration.
My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.